Now let's get on to the fourth step of our journey towards FOL CNF. This is a critical step which is non-trivial, and new. This is called skolemization. So to understand skolemization, let's go through some example and analogy. So what skolemization does is that it removes existential quantifier from the prenex sentence. Only the universal quantifiers are left after this operation. So let's see an example. Okay, let's suppose we have a sentence: for every man there is a woman. So you will encode as a logical form: for all m there exists a w relationship m comma w. Okay, so you say, okay, this is your encoding of your sentence. If I want to get rid of exist, so exist is what is the role of exist, what it is doing. For each m it is finding one w. It looks like what if function, but it is playing a role that you give me an m, I will give you an w, right? So therefore you can model it as a function which takes one man and returns one woman. Okay, so therefore you can replace your extension quantifier by a function. Okay, so you say m f of m, okay? And then you say for all m. You get rid of this quantifier, you get it replaced by a function symbol. Okay, so this idea that existential quantifier can be replaced by a function is called skolemization. The function that is being introduced is called skolem function. Let's prove it through a theorem which proves that this is allowed. In fact, it's correct. So let's suppose f is a formula which has n plus 1 free variable y1 to yn, and there's a variable x, and there is a function small f which does not occur in this formula f. Okay, so let's continue. For each model m prime there is another model m such that m satisfies there exists xf implies f of with skolem function. What is going on here, that in this formula you can see that y1 to yn are free variables, and we have not written any assignment here. This notation means for every possible assignment m satisfies this formula. Another requirement is that m and m prime only differ on interpretation of this new function f. Okay, so let's see how can we do this. Okay, so consider a model m prime naturally, and we will construct m. Okay, before doing that, let us construct an interpretation f prime of f as follows. Okay, so how do I do that? If I get some n tuple d1 to dn, and I also evaluate this, then what do? I take m prime and give an assignment y1 equals to d1 and yn equals to dn, see if it satisfies my formula there exists x in f. Okay, if it satisfies, okay, it satisfies the whatever value that comes out in f, there must be some value that is satisfying, right? Whatever satisfying f, right? So whatever the value, let's say d, satisfies f. Okay, this d must exist because this is true. So we pick that value and return that d. If it is unsatisfiable, okay, so if this does not satisfy, then what do? We some any d. Okay, give any, return any d. Okay, so this way we construct an f prime which is a well-defined function. Using this f prime, we will modify m prime and obtain m. Okay, so you say, okay, we map f to f prime. Since f does not occur in f, we can say that if this guy satisfies the formula, then m prime b also satisfies this formula. Due to the construction of m, now we can say that since there exists x, f is satisfied by m an assignment, then what we can do is that m and the assignment must satisfy this this formula when x is replaced by this function, because the exist and the function f are just running in tandem. You can easily show that this will hold true. Now we can use this theorem further to actually show that these two formulas are equally satisfiable. So again, we have a formula f which has this n plus 1 free variables, and you have exist x and n of them are quantified, and you can say your claim is that if and only if you have this formula satisfiable. How do I prove that? So let's do the forward direction from here to here. So let's say this is sat. Okay, so we pick a model m prime. M prime gives us for all y1 to yn there exists x fx. Okay, now therefore there is m prime satisfies there exists x fx because there was no free variable here, and now there is a free variables here. Therefore I'm saying that for any assignment you pick, this will be satisfied. And so this is okay. Due to the last theorem, we can say that there is m such that m satisfies there exists x fx implies f of f y1 to yn. Now this m and m prime only differ in interpretation of small f, so we can say that m also satisfies there exists x fx, and due to using these two facts I can simply conclude that m satisfies this guy. Now look at the reverse direction. The reverse direction is fairly simple because of the reverse direction it's implication. It's not equisatisfiability issue. We can simply prove via our proof system. We assume one of the formula with the function, and this is the formula by assumption. Then I use for all lm and get rid of my quantifiers. I got this, and I can replace this term by an x and introduce a quantifier exist x. It's up to me. And then we can bring back my quantifiers using for all intro, because in the context these variables are not free. So see, I can assume my formula here and can derive this. Okay, so I managed to prove the reverse direction simply using the proof system. So since the quantifiers are in prenex forms, all exists can be removed using skolem functions. Okay. The skolemization should be applied from out to inside. Okay, and the remove outermost exist first. So for example, in this setting you have outermost quantifier which is exist z. Okay, and it should be the function of all the universal quantifiers occurring before it. Since there is nobody is occurring, then you will get it replaced by a constant. Okay, so you say okay, there exists z, get replaced by c. Now we have another exist quantifier which there exists x. Now which are the universal quantifiers sitting in front of it? Only one, which is for all w. The function we will introduce will have a single parameter, and that parameter would be w. Okay, so let's take out x and replace it by w and a function f. And now this is skolemized sentence in which we have removed all exist quantifier variables. Now we are left to do is finally get to our FOL CNF. The two more steps left and the fairly simple steps. Yeah. Consider the following skolemized prenex sentence. You have a universal quantifier and the formula f. This formula f doesn't have any quantifiers, only atoms and the Boolean combination. You can apply any favorite of ours, CNF transformation, and turn this into clauses C1 to CK. We got this clauses, which is you can use Cython encoding and other encoding, but Cython encoding is a slight problem, introduces fresh variables, and what is the quantification over them you need to worry about. So that issue I will not get into it, but it's good to think about how that gets handled. Then we have this form that the body consists of clauses. For example, in our formula we already had a CNF form because the body had two literals and we have their conjunction. So therefore we don't need to do further transformation in our example, but you can easily imagine a formula where it's not a CNF at the Boolean level, so you can just simply rearrange the formula, turn into CNF form, and you get this CNF formula. Now the next step is the dropping of this universal quantifiers. First thing to observe is, since universal quantifier distributes over n, so we can essentially write these clauses separately and put their quantifier with them. Okay, and well, you may wonder why this is helpful. It helps us see that in the different clauses, the variables appearing have nothing to do with each other. They are independent variables. Within the clauses, they are related to each other. Yeah? So that's how we will see them. And we don't need to write quantifiers anymore, because if a symbol is appearing in your formula, it is a variable. It has to be universally quantified, otherwise it would have been skolemized. So you only get variables that are universally quantified. So you get a bunch of clauses which have atoms of the first order logic, and they may have variables in it. That's all there is left in your formula. Okay? And this is called FOL CNF. Okay, so for example, in our case, if you drop all our quantifiers, we're left with this formula, and then we will say this is FOL CNF. But notice that since universal quantifier distribute over conjunction, this W and these W's are two different variables. Okay? They are not the same variable. So be mindful of this issue.